Hi everyone, here we are, we made it, question 5B, the bonus challenge question. Before we get cracking into this too much, a few logistical points. If this question looks a little different, it's probably because the original written version of this wasn't very clear. So I've rewritten it to try to be a little more clear as far as the system that we're dealing with. If you were to get something like that on an exam and it was kind of oddly written, maybe you're having challenges interpreting it, don't worry. So chances are it was just written a little ambiguous. The best thing you can do is clearly define your system. So this is why I always say, draw me what you think the question is saying. So you draw your system, you label all the parts on it. From there, what can happen is if you happen to, let's say, not get the marks you're thinking you're going to get for that question, you can always bring it back to me and say, hey, look at this question. It wasn't very clear that 500 meters was supposed to be here versus there. You weren't very clear where these runners were supposed to be, whatever the case is. And as long as I can see your logic, and as long as that logic is followed through, you'll get marks back for that, okay? That being said, if the question is very clear and you come up with your own system and you bring it back to me, I might say, no, it's pretty clearly written here. Most students understood it the way I intended. Again, but you are definitely allowed to argue for or come back and ask for more marks. But the big key is you have to communicate how you interpret it on the exam. So while you're writing it, you can't come back to me after and be like, oh, I thought this meant that. It needs, and chances are, as I see it while I'm marking it on the first place, I'll see how you interpreted it, and I'll typically go off of what you said if I feel that the word or the question wasn't answered very clearly. And usually I pick up on that if multiple students are interpreting the question the same way. I'll be able to gauge that myself. Okay, so just a little reassurance that way. Don't hit the panic button when you see a question that's maybe not super clear. Okay, just define the systems, follow through as best you can. Okay, great. So with that being said, let's go into dive into this new question as written, more clearly out for us. And if you haven't done it yet, all of this was kind of foreshadowing to say, like, go back and try it now without seeing the video, and then come on back and watch the video. Okay, great. Well, yeah. Okay, so let's take a look at this new question. So in the above question, so the one where we had a runner sprint for the final victory here, we didn't know exactly where this acceleration period happened. We now know the final velocity for that runner. So in the above question, so 5A, the winner finished accelerating some distance from the finish line. And we knew this. This is what we drew here, but we're just going to draw it again here. Okay. So we have, let's say, we'll go winner in gold. Does that show up? Winner in almost gold. Okay, they have some distance that they travel before the finish line. Let's keep the finish line red. Okay. Yeah, there's our finish line. So we have this winner. So they have some sort of an acceleration period, right? Accelerating some distance from the finish line, but held that final velocity to the line. And then they have some sort of acceleration that is constant. Or sorry, I'm just going to reword that. It's going to velocity. So I'm just going to say constant. Const. Okay, so V const, or we'll end up shortening that to VC. Let's even give that a new color, just to help us keep our systems organized. Okay, great. So far, so good. Okay, held final velocity, and so it's the final velocity all the way from whatever point our acceleration happened to have gone to. The rest of it, which we don't know the distance of yet, maybe it'll tell us in the question, they held velocity constant. And that was VF from the final. Okay, so that equals VF from our first system over here. Okay, that's what that just said. Held the final velocity to the line. Okay, so they won. We're being told they won because 500 meters back from the finish line. So okay, we got more information about our system. So this is 500 meters back here. That would be 0 or at the finish line. 500 meters back, the winner had the second place finisher beside them. Okay, so we got another racer here. Excellent. Now it's a race, right? More than one person. So let's draw that person in. We'll give them a whole new system, maybe up here, just above. Okay. So at 500 meters, they're right side by side. However, the second place finisher tried to, but was unable to accelerate during that time. So for this rider over here, acceleration equals 0. So there was none. Okay. During that time, and traveled the whole 500 meters. So from here all the way to the finish line at some velocity, which we have. So the velocity here the whole time, we can call that average velocity. We can just say velocity, constant velocity, all of it's the same until the finish line was that. How much time, so here's what we're looking for. How much time did the winner win by? Okay, so from that last line, we know we're looking for like t of our winner. We're looking for t of our second place finisher, and we're going to compare the two. Okay. So let's return to our drawing again, reflect on what we know, and then try to figure out where we're getting to. Okay. So what do we not know, and what do we need to know? So let's just address our second place runner here. Okay. So 500 meters. So we got some sort of a let's say second over here. So we have, we know they go 500 meters. Their change in displacement is 500 meters that they run. We know that they have a velocity of 5.2 meters per second for that whole duration of time. No acceleration. So yeah, we can write that down. Why not? Acceleration equals 0. And what else do we know about this person? Second place, unable to accelerate. Yeah, that's about it. Okay. So from here, what are we trying to find? We're trying to find time. So let's go back to our equation sheet and just check it out. Some of you might already see where we're trying to head with this, but if you don't, that's okay. So we're going to look here, and we're looking for something that has two variables we know and variables we know with one unknown. We're always just looking for one unknown variable. So what do we know? We have delta x, we have v, and we need t. So we're looking for something with x, displacement, velocity, and time. Okay. So let's see, what do we have here? Just change in displacement, we have change in time, velocity. Okay, well, this has all three variables, right? We have our velocity, our change in displacement, and time. Okay. So this is looking good. We can use this and rearrange it how we see fit to find what we need. Similarly, this equation below it is the same. It's the same one, just rearranged for us slightly different. Okay, so both would work. I think the easiest to isolate time will be to use this one. Okay, yeah, and again, either would work if you rearrange it accordingly. Okay. So if we go, we start with, let's use a different color. Sure, dark blue. It's in dark blue. Okay, so if we start with our delta x equals velocity times time, and we want to get time by itself, we divide both sides by time, and so that we can get rid of that. And so what we're left with after that is delta x over t equals, solving for the wrong thing there. We're going to do that with v. Divide both sides by v. We can get rid of that term. And this becomes delta x over velocity equals t. Great. So now we're solving for our unknown that we're looking for. We can just plug and play from this point. So let's write it this way. So t equals, again, just kind of continuing on over here, our delta x is 500 meters, right? This is just this term here. And we're going to put that over top of our velocity, which is 5.2 meters per second. And when we calculate that out, that equals 96.2 seconds. Okay, great. So we've already found out how long it took our second place runner to get from 500 meters back to the finish line. Okay, that one wasn't so bad, hey? Great. A brief note about this is if we would have picked some other more longer, let's say complicated looking kinematic equations, what would have happened when we plugged everything in, and I made a note of this on your answer key, but more or less, if we would have rearranged the variables to get what we want, in particular from this equation here or this one, once we put in zero acceleration as well as our zero final displacement, because again, this would be 500 meters here, this would be our 0 meters there, because it's 500 meters back, so we just switched the orientation there of our coordinate system. Essentially, we'd end up with an equation, again, especially if we isolated for t, would be looking exactly the same. So I guess what I'm trying to say is reassure you a little bit that if you happen to pick an equation that's not exactly the most simplest reduced version, you can still get there. All those variables are typically are interrelated. Yeah, just as a side note there. Okay, so again, if you want to see how that's done, we can walk through that. That's fine. But just for the context of this video, we'll keep pressing forward. Okay. Okay. So we got our time for our second place, which is 96.2 seconds. Great. Now on to our winner. Okay. Great. Now this system gets a little more complicated, okay? So I'm going to try to keep our sketch or schematic in view. And we're just going to deal with two different segments now. Now, why are we splitting up this segment? Well, the reason for this is for this for the initial part, and we worked with this in part A, right? If we scroll up here, so part A is telling us a lot of information here. Okay, initial velocity, acceleration rate, and time, but only up until some point, and we don't know where that is along that 500 meters, which we now know. We didn't know at this point in time. We know now they're 500 meters away from the line. But where does this acceleration, this 5.4 seconds, where does that put us? Does it put us there? Does it put us here? Does it put us right in front of the line? We need to figure that out. Okay, so we're gonna scooch on back here, try to collect all the information we know in our new question here, just so it's easier to track. But again, most of this information refers to what we'll call our first system, or our acceleration system within that part. So Excel, or part A, or I, however, I think in the answer key I have I for this. Okay. So for this phase, we know that VI was equal to 5 meters per second. Again, we're just, I'm pulling down this information from up here. Okay. We know we solved for VF in that one, and that was 6.1 meters per second. So sped up essentially 1.1 meters per second during that time. Okay. Our time was 5.4 seconds. Again, we just are pulling this information from here. We had an acceleration, which was 0.2 meters per second squared. And what we're solving for is our displacement. That's unknown. Okay, so we were given a lot of variables, a lot of information here. Let's just make sure we got it all. Time, meters, yes. Okay, great. So again, what we're trying to solve for is, what's a nice bright color? Is this our acceleration, our go section here, speeding up. Okay, section A, that's this part here. Again, we don't know how long this 5 seconds or how far this 5 seconds will take us. That's what we're figuring out. Okay. So now we know our system. We collected all the information we know and all the variables we have. Let's look at the equation sheet. Okay, so we're back here checking out all our possible equations. Now we have quite a few variables, so some of the simpler ones are probably not gonna work. Sometimes you might be able to see that they do, but recall that regardless, if these will always reduce the way we need them to fit. So let's look down at these. Again, we need something with change of displacement. So this has a position, initial, and final, so we could figure out displacement from that. This one has position, initial, and final, so we could find displacement from that. This is delta x when we just see x by itself, so that would have a potential displacement that we could use. The one for sure that we won't use is this, okay? Because we need to solve for delta x, and it doesn't have it, so ignore that one. So we've reduced down to 3 possible equations here. Okay, from there, what are we going to do? Well, we're going to look for the one that has most variables that we have, because that gives us more information, okay? So from here, we know we have velocity initial and final. They're both different, so we need to include those if we can. This equation has the initial and final velocity. This has initial and final velocity here as well, okay? Now this doesn't. Now, I'm going to make a case for this one and use it more from like a test-taking strategy, because ultimately, well, again, this doesn't have time in it, and we know we want to include some sort of amount of time in here. This one does, but or this doesn't have any acceleration. So again, ultimately this has all of it in. But even if it didn't, I would say I would debate for you to use this equation, largely because if you had to calculate v final and you for some reason got that wrong, that would carry over into this question. Now you'd only lose part marks. I'd see what you did, the logic would check out, and I'd just carry that forward as you calculated it. So it might be a half mark somewhere out of the whole question for you. But again, if you just wanted to be double sure, that'd be a good one. Okay, we're using this equation. So let's copy that out, and then we'll solve for, we'll see how we solve for the change of displacement for this first section. Okay, so we got x equals, and that'll be x final versus x naught or x initial plus velocity initial or not. Again, both mean the same thing. T plus half of at squared. Okay, great. Okay, now again, as I was saying before, we want to try to figure out displacement. So what our first move is going to be is to create delta x essentially for ourselves over here on the other side. Yeah, again, it makes it a little bit easier, I find. Yeah, so we can have right, we have x final minus x initial, which that just equals delta x, right? That means the same thing. So we'll carry on from there. This is canceled out. So we have velocity initial times t plus 0.5 at squared. Okay, feeling good about that. And let's start putting in some variables. Yeah, let's continue with that color. Okay, so our v initial is 5 meters per second. Our time frame is 5.4 seconds plus 0.5 times acceleration, which is 0.2 meters per second squared times time again squared. Okay, and now we just get to plug and play. Okay, so when we go 5 times 5.4, I have it calculated here. It's 27. And when we multiply, so square this first. Anytime you see an exponent, according to BEDMAS, right? Get that out of the way as best you can. So once we multiply that all together, looks like we have 2.9. Add those together, and we have 30 meters. 30 meters. That might have been rounded up with 30 meters, okay? Yeah, that would have been rounded up. Yeah, good, okay. So what does this mean, 30 meters? What are we talking about here? What does that mean? Well, it means the change in displacement. Okay, we got to go back up to our system here. So it means the acceleration period lasted from 500 meters to a change of 30 meters in. Okay, so we overshot here a little bit with that. So 30 meters of acceleration before all the rest of this was held at constant pace. Okay, so let's just complete our system diagram here. You don't have to go back and change it. I'm just trying to do this to be illustrative, help out. Okay, so what that means, if we go 500 minus 40, it means the rest here is 470 meters. Okay, so 470 meters. That's what we have from this point to the finish line now, where the constant velocity is all the way through. Okay, so let's move forward and look at that system. So now we have this new system that we're looking at where we have constant acceleration. So we can write constant velocity. And now this should be ringing some bells to something we did earlier, right? So this second place finisher also had a constant velocity all the way through. Okay, so we can use the same approach as we did here with our time equals displacement over velocity. Okay, we're just going to pull that down, right? Time equals displacement over velocity. Because again, if we look at this new system here that we got, we know the displacement now. We know our velocity that is constant. It's the same velocity all the way through. It's not changing any way through. So we can use our final velocity that we calculated. Again, we're going to have to use this one. Okay. And yeah, carry that through. Because again, they accelerated from VI to VF. And that's what we calculated. Where did that go? 6.1. Oh, and question A, sorry. Absolutely, yeah. Question A. What is our final velocity at the end of the acceleration period? Okay. I knew we had it somewhere. There we go. So 6.1. And to carry that down, so again, VF, but it's constant to the finish line. So that equals, 470 meters over our 6.1 meters per second. When we calculate that out, that is going to give us 77, and that's in seconds. Okay, so here we are. We figured out 77 seconds. But if we go back up to our graph here, remember we have two parts to this. We have an acceleration and a constant. So what we found out with the 77 seconds is this one right here. But if you remember all the way back up at A, wow, that's getting really busy here. We still have this one segment that was 5.4 seconds, right? So that's this part here. So this is 5.4 seconds. So now we need to add those two parts to see what the total time is from 500 meters to the finish line. Because again, we're trying to figure out how much the winner won by as far as time. Okay. So here we go. So we got our acceleration period plus our constant velocity period will equal our time total. So our acceleration period was 5.4 plus our constant velocity period, which was 77 seconds. And those two together are 86.4, I believe. 82, sorry. 82.4. Okay, seconds. Yes, okay. So that's our T total. Now, this is the moment we've all been waiting for, right? We got our T of our second place finisher plus the time of our winner, or sorry, minus, because we're looking for the difference, right? You're looking for the difference between these two, and that will equal how much time the winner won by. Okay, so let's do that. Our second place finisher took 96.2 seconds to run that 500 meters. 6.2 seconds. Our winner, we said, took 82.4 seconds. And so the difference between the two, it looks like it was a really, really close race, 13.8 seconds. Which again, if you think about someone passing the line and counting 1 and 2 and 3 and 4, it's maybe not that close of a race relative to like a 100-meter sprint, but if you're talking about like a long distance race, that could be pretty significant, okay? Or kind of close. Okay, so there we are, 13.8 seconds between the two finishers. Again, multi-step, and probably the most crucial part out of everything would have been drawing this system and making it clear what was going on here. I know it looks very scribbly right now. Leave yourself some room to do this. Leave yourself to have that. Make sure you identify your systems however you want to name them. It could be A, it could be B. Sometimes letters get a little confusing. Numbers will mix you up. But if you use a subscript like S or W or something along with a lot of your variables, that'll help you keep organized, and it'll help me figure out and follow your logic as you work through, okay? Especially if you're like, make this a very capital A and this is a big capital B and C, and you put those subscripts down on the different components that you're working on, okay? Okay. Hopefully that was a helpful walkthrough. Sorry if it got a little busy, but again, you have the power to go back and rewind and try to see what I was doing at each moment. Hope that helped. As a third or fourth reminder, this would purely be a bonus question. This wouldn't be something in the main content of your exam, okay? But hopefully maybe it tied a few points together or helped you figure out maybe how you might organize simpler coordinate systems before you start approaching a question. Maybe you had a bit of an aha moment in trying to figure out how to pick out which equation to use. But yeah, regardless, I hope you got at least a little something out of here that you can apply to, say, more of like the main bulk of your exam versus, say, a bonus question. If you did get this and you get a bonus question like it, great, go for it, have fun with it, and yeah, enjoy the bonus marks that you get from that, okay? All right, best of luck, happy studies, and bye.